In this sixth lecture of special relativity, we introduced the Doppler effect and derived the formula to calculate the Doppler shift. The Doppler effect is a phenomenon arising when observing propagating waves in different inertial frames. It was first reported by the Austrian physicist Christian Doppler in 1842. In order to fully grasp the effect, we first revised the main quantities characterizing wave propagation in a medium: the wavelength lambda, the wave amplitude A, and the wave period T. There are other physical parameters often used to describe the wave motion: the wave number k, its frequency f, and its angular frequency omega. We also discussed how wave fields are usually represented using complex functions, and the meaning of the phase velocity c. We then discussed that a wave signal usually needs three entities: an oscillating source that generates the signal, a medium that propagates it, and a receiver that receives the signal. Usually, we consider source and receiver not moving with respect to the medium. But what if this does not happen? In order to describe the Doppler effect, we specified a convention. We said that the oscillating frequency of the source is called the proper frequency, and agreed on one convention, that is the sines, to describe the velocity of the source and the receiver with respect to the medium. We first considered the case of a constantly moving receiver and a steady source with respect to the medium. The frequency of the signal perceived by the receiver increases according to the formula if the receiver moves towards the source. Then we consider the case of a moving source and a steady receiver with respect to the medium. Here, the wavelength of the signal transmitted in the medium increases accordingly to the formula for a source moving towards the receiver. By combining the two cases, that is, by allowing both the source and the receiver to move with respect to the medium, we finally obtain how the frequency of the signal is modified, that is, the Doppler frequency shift. Finally, we considered an example where an oscillating tuning fork, kept steady with respect to the medium, emits an A note. Assuming that the receiver perceives a G note instead, we computed its speed and direction with respect to the medium.